Hi, my name is Saurav Behera, and for my Physics 2211 Lab 5, I decided to investigate the motion of a falling slinky. To provide a brief overview of the lab, I am going to analyze a video of a stretched slinky being dropped from a height above the ground. And my goal is to investigate the effects of gravity and drag on the motion of the slinky and validate it in my findings. I'm going to produce two deliverables in this lab, the first being a position versus time graph generated by tracker, which tracks the center of mass of the slinky as it falls. And I'm also going to generate a position versus time graph generated by my GlowScript using a computational model that takes into account the equations of drag force, force of gravity, and tension force. The principles that I used in my computational model are Newton's second law, which I used to update my position and velocity. I also used gravitational force, which is weight is equal to negative mg times j, which is the position vector of gravity, and drag force, which is equal to negative bv squared times j, where b is the proportionality constant and j is the direction of the drag. Using tracker, I was able to track the motion of the slinky falling from rest. I set a center of mass of the tracking point to be at the bottom of the slinky. Center of mass is indicated as a red dot in each frame, and its overall motion moves in the negative y direction. The corresponding tables and graphs to the right show the center of mass's position and time. Note that the bottom of the slinky remains motionless as the top of the slinky falls towards it, and once the top meets the bottom, they fall together. The initial mass is estimated at 0.25 kilograms, the fully stretched length of the slinky at 1.75 meters, and the initial position of the red center of mass at 0.03, negative 1.218 meters as stated by the tracker. To set up my computational model, I had to include a few of the initial conditions. So as stated in the slide before, I had included the slinky's mass, position and initial velocity, and used the acceleration due to gravity as the constant of 9.8 meters per second, and the direction of gravity as 0, 1 in the y direction. Now the drag coefficient was found by trial and error to try to match up the scale of the drop to the computational model. My computational model ran through two simulation loops, one where it ran through the time before the bottom of the slinky moved, and then one loop where it ran the time after the bottom of the slinky moved. But in both screenshots, I included the forces present on the object during the time. So for the first loop, it included gravity and tension, and for the second loop, it included gravity and drag. And I also included the velocity and position update formulas that I went over in the introduction and principles used section. After running through my computational model, I went into a spreadsheet and was able to plot the position versus time of the observed video using tracker and the computational model together. And as you can see, they are very similar, albeit some slight differences, which can be due to outside factors such as wind and other forces that weren't accounted for, as well as a slight force of tension playing a role in the drop component that I didn't include in my computational model. And the bottom is initially stationary, similar to the video, because tension and gravity are equal in magnitude, so in the free body diagram that's created, they essentially cancel each other out, and the object is not in motion. But once the top and the bottom fall together, gravity and drag act on the slinky and have it move in the negative y direction as shown.